Cool. Awesome. Well, thanks, David. Thanks, Chris, for kicking this off and for the invite. We really appreciate it. Being able to talk to folks about what we're doing at TrustPoint, the impacts we have or will have on the economy and some of the systems, not the least of which is autonomous cars and kind of the next generation of transportation. And we always welcome that opportunity. So first off, thank you. As far as quick intros, my name is Patrick Shannon. As you see on the screen there, I'm the CEO and one of the founders of TrustPoint. My background has primarily been, or almost exclusively been aerospace. And in the aerospace sector, starting in the defense side, and then worked my way over into commercial, into what we call new space, and then eventually into the new space portion of the GPS world. And yeah, and that's just a little bit about me. My background is technical originally, but I'm on the business side for about the last 8 to 10 years or so. Chris, you want to do a mini bio?
Yeah, sure. Patrick and I have known each other for about 6 or 7 years. When he and I met, I had just finished my career as a U.S. government employee. I had worked across the DoD, ultimately landing in a job leading research and development for some of the government spacecraft, learning a lot about small satellites and what they can do, and got excited about taking commercial small sat technology and applying it to dual use problems. That led me to found a company called Hawkeye 360, which has launched some satellites to map the RF coming off the Earth. I enjoyed the early stages of a startup so much that when the opportunity arose to join Patrick in building out a commercial complementary PNT solution, I jumped at the chance. I am from Northern Virginia, so I still live in Chantilly. We've just stood up our office in Sterling, and we are hiring. I have to put that plug out there for anybody who's interested. And Anne's going to convince me to cross the border over from Loudoun County into Fairfax enough. So yeah, we appreciate the opportunity to talk today. And with that, I will show the slides, Patrick.
Sure.
Go from there.
Great.
Can everybody see them?
Yep.
Great.
Looks good. There we go. Awesome. So I'll go ahead and jump in here, go through this. We've got a bunch of slides here. Some of them are TrustPoint specific, and some try to get into the autonomous car side of things. A lot of it's high level to help initiate the conversation, and we're looking forward to questions and comments towards the end. So first off, a little bit more about the company. So TrustPoint, we're a VC-backed company, and what we are off doing is building a fully commercial GPS service. And that includes building our own constellation of spacecraft. So we'll be building a constellation of CubeSats in order to provide new innovative signals in the GNSS space, Global Navigation Satellite Services, to improve upon performance, security, and reliability, all with an eye toward a few key segments, autonomous navigation being one of them, infrastructure management, and then augmented reality. Next slide, Chris. And I would guess that most folks on the line and recognizing some of the names of the attendees are aware that the GPS really permeates our society and our economy for all intents and purposes. It's pretty much in everything. And actually, I would challenge folks to look around their home or their office and try to identify devices that maybe don't have GPS built into them for some form or factor, or don't rely on GPS in some way. It does play a major role in transportation, aviation, the public transportation, in trains, global shipping, but it also plays kind of a less obvious role in EMS services, financial transactions, telecom, and a lot of apps. Everything from Google Maps on your phone helping you get to a coffee shop you've never been to things like Pokemon Go that kind of took the world by storm a number of years ago that rely on GPS for the gaming aspects. Next. And when we look at GPS, it's done a lot for us. In fact, it's been quantified that if GPS were to go out, you're talking about $1 billion per day of economic damage or loss here in the United States alone. You can imagine it is a global system. If we were to look at the global metrics, you're looking at numbers that are much, much bigger. And in fact, the UK even said, a smaller country with a smaller economy, they were looking at something close to $1 billion per day, or it might have been even £1 billion per day of economic loss were they to lose GPS. As you can imagine, there's a lot of tie-ins. The thing to kind of take away, though, is what it does today for us is not everything we need. And in fact, if we're going to go kind of achieve the vision that a lot of us technologists have of what tomorrow should look like, GPS isn't going to get us there. It falls short. And it falls short in a couple of key areas that specifically TrustPoint's focused on. And there's a lot of other tech companies that are focused on other different pieces of this, building camera systems and radar systems and altimeters and different types of games and things. But this is where we sit. So if I just start, top left and work my way around here, self-driving cars. We have pretty well proliferated things, that assist drivers today. We have automated cruise control that keeps distance with the car in front of you, automatic braking systems, lane departure notifications, and then some of the newer cars have lane centering. But that's not really the autonomous experience that we're looking for. And we're still pursuing that. We're looking for that experience where we call the autonomous car like an Uber, like a Lyft. It shows up, we can spin our bucket seat around, hang out with our kids on the way to drop them off at school, hang out with our buddies on the way back from the bar, or take a nap on our way to family for the holidays or something to that nature. And we don't quite have that. There are limited operations in various cities. Google has some operations, Cruise has some operations, but they're heavily observed. There's human in the loop that can be brought in very quickly as needed. And those systems are expensive and difficult to operate, which is why they're limited in scope. And so we want to proliferate that type of experience. Same thing with drone delivery. And I think this is very interesting. Drones don't have the access to the same technologies that cars do. And they're even more dependent on GPS than land navigation systems. But if we're going to pay a premium to get something delivered, in the next 10, 15, 20 minutes, or even on the B2B side, get a very high value package point to point delivered across a number of states or even across national borders, we need to know that package is going to arrive on site very quickly, very efficiently. And it's not enough to say, hey, I dropped it on your property. Right? We don't want to go outside and spend another 10 minutes looking for it or trying to get it out of some tree somewhere. You want to know that exactly where it is, at the bottom of your steps, near your front door, in your backyard, on your porch, that type of thing. Urban air mobility, this is a step up. These are your flying cars, which kind of very futuristic here, but we're not that far away from it. And this particular sector is super interesting because like the drone side, they don't have nearly as many phenomenologies to depend on for navigation. And if we're going to proliferate these systems and go from, there is autonomous landing, for instance, and autonomous takeoff for large commercial aircraft and some smaller manned systems, but they're limited to where that happens, to actually a few hundred airports globally. We're going to move to urban air mobility and have hundreds of thousands of vertical ports where there's no pilot in the loop for takeoff, approach, and landing. We really need really high precision, high reliable capabilities like next generation GNSS. That's where we're going to come in. And of course, immersive augmented reality. This is another one. There are both business as well as gaming applications, but we want to move away from something like Pokemon Go, which is just you on a Google map on your phone, to something that's fully immersive and in an outdoor scenario where you can put a fully immersive 3D environment superimposed upon the real world and have a nice experience, whether that's a productive work-like scenario or a gaming scenario. I think it's indifferent. People want both. And that's what we're trying to achieve here. Next slide. So the problems of GPS and kind of positioning, as it were, we break these into 4 parts. And I think you can, skin this cat 1,000 different ways if you want, but we like to talk about it in these 4 because they're easy to understand. And they do group maybe 90-95% of the real issues that come out that are very specific. The first one's accuracy, whether it's on a car or an aircraft or other systems, how precise can we be? And GPS today, depending on how you implement it, can't be as bad as 10 meters in bad environments without the extra added phenomenologies like PVP and RTK, or it can get down to decimeter and centimeter level with different systems and data entries. But those are either very expensive, difficult to achieve that accuracy in the time domain. So you might be able to achieve it, but only after 10 to 20 minute integration, or RTK, where you got to deploy equipment everywhere you want to operate, not just on the vehicle to get the accuracy you need. So the accuracy is an issue, and that's something we want to address. Easy to disrupt is another one. We traditionally think of this as jamming. GPS is a very quiet signal. It's a quiet signal for a couple of reasons. First off, it's very far away. The spacecraft themselves are way out in MEO orbit, 20,000 kilometers away, and the power they have is pretty low. You're looking at something, that's the equivalent of 60-watt light bulb. And there's, it's not a great analogy, but it's far enough away that when it shows up, it's an incredibly quiet signal. In fact, it's below the noise floor. And so if you've got an RF background, you know that you can't actually just directly observe the signal. You have to search for it in a deterministic way, stepping through big search space to get that signal. And because it's so low power, it's easy to jam. And that's both adversarial, whether that's, the Russians in Ukraine, the Syrians in the Eastern Mediterranean, the Chinese in the South China Sea, or inadvertent, which is multipath in the bottom of an urban canyon, in a deep city like Manhattan or Chicago, now where signals bounce off of buildings and come at you from all different directions and kind of self-interfere. You also have the faking problem. This is spoofing. This is where you have an adversary that sends out fake GPS signals. And this is very important. A lot of folks don't recognize this, but GPS used by the civil and commercial world is completely unencrypted and unauthenticated. And so what you're looking at here is, historically it took a state actor, but now a couple of grad students with a laptop and a software-defined radio can broadcast fake GPS signals. And you can imagine if you're sitting in an autonomous car driving on the highway at 80, 90 miles per hour, you don't want some up jumped high schooler messing with you as you drive by their high school and they're doing a project out in the football field, for instance. And so you want to increase upon the capabilities there. And the last one's slow to resolve, responsiveness, otherwise known as time to first fix. How fast can we get a positioning and timing solution? But not only that, is how fast does it take to get to the precision timing and position solution. And that's another thing that's a big problem, especially when it comes to autonomy. But that's where TrustPoint comes in. Next slide. Awesome. So the solution, TrustPoint looks at our particular mode of addressing those four problems in two ways. There's the infrastructure layer and the signal layer, or what I like to call the RF physical layer. In the infrastructure layer, this is where we're deploying constellation of notionally 300 spacecraft. These are very small CubeSat class, 10 to 20 kilograms, and they can be built for hundreds of thousands of dollars. These are not like the GPS satellites that the Air Force launches, where a single satellite delivered to orbit is close to $600 million. We're talking about an entire constellation of 300 that can be built, deployed, and operated for roughly less than half of a larger single GPS satellite. And innovating on that infrastructure layer, it also gives us new orbits, new positions to broadcast those signals from. And in particular, we're in low Earth orbits. We're much closer to the Earth, about 20 times closer to the Earth than the GPS system. But our signals coming off the spacecraft aren't too different in order of magnitude than the signals coming off the GPS system. And to that extent, the signal arrives at the Earth and can be much, much higher power. And that improves a lot of things. It improves the anti-jam capability, improves the accuracy, and other stuff on that nature. Now, the other side of our solution is the signal processing, the RF physical layer. What does the signal itself look like? What are the data elements built into that signal? And how do we process that signal? And I heard a great example the other day, related to the cell phone industry. The cell phone industry, turns over every 3 to 5 years. And when we start looking at how the signal structure, how we go from 2G to 3G to 4G to 5G, we get much, much more capability. And all those changes from 2G to 5G have happened in the last 20 years. Now, if you look at GPS, you look at the signals that we're using. In the last 20 years, we've deployed new signals. We've deployed new signals recently that were created 20 years ago. So we're working on stuff that is 2 decades old, even though these new signals called L5, or even the Galileo E5A, E5B, and some even the Chinese signals, these are things that were conceived of over 20 years ago. And with that in mind, we're really leaving a lot on the table when it comes to technology. And so TrustPoint is innovating on the signals themselves, how they look, how they operate, what you measure off them, the data elements embedded. And if you combine those two elements, the infrastructure and the signals, we believe we're fully going to be addressing a majority of the problems we saw on the previous slide, increasing time to first fix, responsiveness, accuracy, the robustness in the case of jamming or unintentional interference, and then the security side. Getting us an encrypted signal for the first time in the civil and commercial world And not only that, but taking it beyond just straight encryption into authentication and other anti-spoof methods. Next slide. Right. So let me transition here quickly to how we see TrustPoint, Leo PNT provider, kind of starting to play in the autonomous vehicle world. And it's very easy to jump to navigation and say, a car driving around a city needs to know where it is, and it uses GPS, a higher fidelity, more secure, more reliable GPS solution to do that. But I'll actually take it 2 steps back, and there's a couple other layers of the ecosystem that TrustPoint is going to play a major role in once we get deployed that also support autonomous vehicles. And it starts with mapping. So if you think about mapping, you have cars that drive around cities that are taking maps. It started with Google Maps, and cars like Mapbox and other companies are mapping the world in 2D and 3D. They're shortly moving, and a lot of this depends on regulatory, from cars to drones. Part of that, a drone can move faster. It can do a little more in the 3rd dimension. And you could potentially, these systems are pretty light and low cost. You could potentially get them out there more frequently, so you can update the maps. And a big aspect of the map is knowing the sensors that are making the map, whether they're optical or LiDAR or radar, knowing where that sensor is in the global reference frame. And right now you do use GPS, but what you can do is, GPS has certain limitations, both on accuracy as well as availability. So what you can do is with TrustPoint, you can increase the position knowledge and the security of that sensor itself. So what you end up having is a better map, quicker maps, more dynamic maps, things that are lower cost at a higher fidelity. And so we see TrustPoint playing a role there in the mapping side. Now, another layer is the middle layer, and that's communication. And a lot of folks don't think about this too much, but the cellular phone industry is and the networks that we use on those are incredibly dependent on global time synchronization. And so we're talking about all of these cell towers tying themselves back to GPS to get time. So not position, but time. And that level of synchronization between the cell towers allows us to make really good use of the bandwidth to have high data rate communications between 2 devices, to use very sophisticated protocols to push lots of bits, to have lots of users using the same spectrum. But that's only doable with a lot of synchronization. And the 5G world right now is doing okay with GPS. They have things called macro cells. That's a traditional cell phone tower. You might have a couple in a city, 1 or 2 in a rural town, but we're moving away from macro to micro, and then eventually to what they call femto cells, which are more like Wi-Fi hotspots. They'll cover a street corner, or they'll cover an office building. And when you start looking at that, they need the same high fidelity time synchronization that you get in a large cell, but they can't spend the money. So they can't go buy a geodetic antenna. They can't go off and get timing synchronization, high fidelity timing synchronization module. And they want to be more secure because there's more and more life critical activities going over these networks, whether it's EMS communications, or for instance, updating those maps in your self-driving car. And so TrustPoint as a PNT service, position navigation and timing service, also supports communications that come back to those cars. And whether it's the car communicating back to a server to get an updated map for an area it's going into, or even cars talking to each other in the 5G protocol, V2X, which you guys are aware of, also needs to be synchronized. And so that's where TrustPoint plays a role. And then, of course, finally, navigation, giving a car really high fidelity information of where it is, localizing itself on a map and knowing, okay, I am on this road, I'm not on that road, I'm in the right lane, not the left lane. And that's going to be very important, especially as we move to proliferate these systems. And like I said, spin that bucket seat around and do things other than watch the road and watch the vehicle. Now, one of the questions is what's keeping us from getting there? So Chris, if you go to the next slide here, and this is a very rudimentary discussion of reliability. And it's a great place to start. There's whole conferences, grad student programs, textbooks written on autonomous driving and the reliability and the difficulty. We just start to touch on it in this presentation, but to give you a taste of how difficult it can be, you have highway lane level accuracy. And historically, people have kind of talked about, half meter, a couple feet on either side, get yourself in the middle of a lane, you're moving 80, 90 miles per hour. You stay in the middle of that lane and you're pretty safe. That's not too bad. When you get down to cities, those lanes start to shrink. You get, pedestrians and sidewalks. You get things like trash cans that you're expecting, that you wouldn't expect on a highway. And that city lane accuracy is going to shrink. And it's shrinking more and more because we're also trying to increase the capacity of our roads. Now, getting those accuracies with today's GPS technologies is feasible with things like PPP or RTK or combinations of those. Now, PPP, it's an integration technology. It takes sometimes as many as 10, 20, or 30 minutes to get down to a decimeter or a centimeter level accuracy. And so it takes time to get there, and you lose that accuracy if you go, through a tunnel or in and out of a parking garage, or you turn your car on for the first time, for instance. And so it's not a great method for getting that accuracy. You can also do something called RTK. This is where you deploy, a priori sensors to an area, and those sensors look at the environment, derive parameters about the GPS constellation, and then broadcast those what we call corrections or differential satellite time and ephemeris or differential corrections to users so they can get a higher precision GPS fix. That means you have to deploy hardware to those areas. And yes, we can easily deploy hardware to cities, maybe even some suburban areas, but being able to deploy RTK to all the rural areas globally is a very difficult task. It's a very expensive task. So those existing systems don't work. Now, when you start talking about accuracy, it's very easy to say, okay, we can get that accuracy. Maybe we don't have it all the time. Does that really matter? Well, it does matter. Reliability is king when it comes to manned vehicles and manned transportation. And so when you start talking to the regulators, you have a couple of different areas that are looking at, okay, how do we measure reliability? And these specifications and protocols and procedures have been developed, and you can do the math and determine how reliable your system is and the numbers you need to achieve to where you can, claim to a regulator, I want my passengers to turn their bucket seats around is very high. We're talking about 99.69s after the decimal place level reliability. And that is hard. Chris, if you click once, what that ends up being is you're looking at a navigation or localization failure once every billion miles. And that's an oversimplification of how to describe that level of reliability. But to give you just a slight feel for what a billion miles feels like, if you're only going to have one failure in a billion miles, you're going to have to do a lot of driving. Now, it's fleet level, so it's not a single one. But if you were a single car, what does a billion miles look like? Click. Is it twice around the Earth? The Earth is, I think, 24,000 miles around? No. Is it 50 times? No, it's not 50 times. Is it 100 or 1,000 times? No, it's not. It's actually closer to 40,000 times. So you'd have to drive around the Earth on the order of 40,000 times and experience only one failure. Of course, this is not really conceivable. You could take the New York, LA trip, which I think you'd have to do 350,000 times, one way to get the same number of miles. And in that amount of driving, you want to experience a single navigation localization failure. And again, slightly oversimplified situation, but that's the level of reliability we're pushing for. And if folks go, that seems crazy, do we really need that? The answer is yes, we do. We drive many times that number of miles every day for the entire community. And if we want to proliferate autonomous cars, we don't want the accident rates to go up. We want the accident rates to come down. We want speeds to go up. And when you talk about increasing speed, you're reducing the reaction time of the system to obstacles and other things in the environment. And so you even want it higher than that. So I think that this 1 billion miles kind of analogy is really just a starting point. We're going to be pursuing and surpassing that to really proliferate systems. Next slide. Now, getting there is not a silver bullet style approach. This isn't TrustPoint deploys. We provide a better set of GPS signals, and all of a sudden, autonomous cars are proliferated. But it is going to help a lot. If you look at a car, they navigate and sense their environment with a number of phenomenologies: LiDAR, radar, optical, even sonar and ultrasonics. They look at their wheel rotations. They look at vibrations in the road. All these things can be fused to provide a navigation solution, both localization and path planning, route planning, and things like that. But GPS is tied into all of those things pretty heavily. Like I mentioned, it starts with the mapping and communication aspects of the infrastructure that allows us to know, okay, where is a road? Where is the curb on this upcoming turn? And accuracy, of course, is very important in that regard. Knowing where the car is compared to that curb, knowing where the car is compared to where you're supposed to stop on a stop sign, and other things of that nature is very important. And the accuracy is going to be a big part of that. Now, things like LiDAR, radar, they can tell you, okay, I'm in the middle of the road or not, but they're a local sensing solution. They're not going to say, okay, I'm on 45th and Lex in Manhattan, for instance. they're just going to say, I'm on a road and I'm in the middle of it, or I'm in the left lane. And so in that regard, achieving the reliability for that localization comes from GPS. And GPS is also one of the few all-weather solutions for knowing where you are. Other systems suffer performance degradation in poor weather, whether that's rain or fog or snow. And things like LiDAR and radar are also very expensive. And we'll talk about costs in a second. But yeah, so accuracy is important. You also have to work on availability. Is your solution, your fused navigation solution, available everywhere? In rural areas where maybe roads aren't well mapped or not well defined, they're a gravel road through a farm field, for instance, and that might be a main thoroughfare for the community. But it is, it's not something that's really well mapped or really could be really well sensed. Urban canyons is another area we want to increase capability down at the bottom of these cities that have very tall buildings. They're very close together. And further, is the system available only regionally, only locally, or is it available globally? Can you take the same hardware that you're putting in an autonomous car in San Francisco, also do that in New York and Chicago, but then move it to London and Rome, and then move to Singapore and Shanghai and Taipei? All these things matter to hit that reliability. The other thing is responsiveness. Do we have that solution out of bridges, out of tunnels, out of parking garages? Do we have it in adverse conditions? I talked about the weather issue, but there's also RF interference. And we've talked to folks that have experienced GPS outages as they go by factories and other things of that nature. And being able to provide a set of signals that helps there is also another important path. So, and there's a common reference, can we make sure everyone's talking the same language and the same reference frame? Cars to the environment and cars to cars. And that's also very important to achieving reliability. The integrity side is also utmost important, and something that honestly we see as very low-hanging fruit. Like I mentioned before, civil and commercial world do not have encrypted authenticatable signals. And that's something a commercial company like TrustPoint is going to be providing. And then finally, can you proliferate it? It's one thing to have a solution, it's another to make it accessible to the world. We don't want, just the uber wealthy driving around self-driving cars, being able to afford, the uber automated version. We want that for the common man. That's how it's going to have the impact on society. It's how it's going to have an impact on our life. To that regard, GPS's score on this very oversimplified report card is pretty low, 2 of 7, and TrustPoint. We're pursuing what we believe on this front to be a 7 of 7 score. So. I think we have, I think that's about it, Chris. Click through there. Yeah, there we go. Thank you for the time. So I think I went a little long, but hopefully that gives you guys a good sense what TrustPoint's up to and how our particular commercial PNT solution, CNS solutions, is going to be playing a bit into the autonomous car sector.